Hello everyone. Today we will talk about the boundary condition. So what is basically boundary condition? Boundary condition is to control the degree of freedom of some of the nodes of the bodies in such a way that the behavior or motion of the bodies are very close to the reality which we do in the simulation. If the boundary conditions are not realistic, the result of the simulation will be far from the actual motion or behavior of the body, and the result what we get will not be realistic, and we cannot depend on the result from the simulation. The deformation, the force reaction, the stress strain can be unrealistic, and that's why the applying the correct boundary condition to get the correct result from the simulation is very important. Some of the boundary conditions present in ANSYS Mechanical are fixed support, displacement, remote displacement, frictionless support, compression only support, cylindrical support, and elastic support. Fixed support is a boundary condition which we can use to completely constrain node or face at any fixed position. Then displacement and remote displacement. So we will talk about the displacement and remote displacement boundary condition. What are the different what is the difference between the displacement and the remote displacement boundary condition? So when you have a displacement boundary condition, so for example, if I select this face and apply the displacement boundary condition on this face, I can control translational degree of freedom, like which is x direction translation, y direction translation, and z direction translation on each node of these faces. Okay, but it doesn't give the ability to control the rotational degree of freedom of the nodes. Example, rotation in x, rotation in y, rotation in z. Okay. When you apply the displacement boundary condition, each node of the face will have the constraint applied by ux, uy, and uz. Okay, and in remote displacement, when you select this face and apply a remote displacement on this one, first a remote point is created at the centroid of the selected face. Okay, and this remote point is connected to the selected nodes. This remote point, whatever will be created, will be connected to all the nodes through the constraint equations. The remote displacement boundary condition control all 60 degrees of freedom. So for that remote point, we can control the translational degree of freedom and also the rotation degree of freedom. Okay. So to understand this, how the different boundary condition affect our result, we will be doing a case study. Okay, and we will perform a displacement boundary condition, some simulation where we will take a blade of the fan and we will try to have a different boundary condition. Like for example, in first case you can see only x degrees of freedom will be fixed. Second case, x and y will be fixed at this face, and in this case x, y, and z will be fixed. Okay, and then we will perform a model analysis and we will see the results, how this affect. Then we will also perform the similar case with the remote displacement boundary condition. Okay, and then we will try to look for the result. Okay, so now what I have done here for this workshop, I have created a simplified geometry for the blade of a fan. So this, you can imagine, this is a fan, one of the blade of the fan this is, and from this face this is connected to the rotor. Okay, now we are going to perform model analysis for it. Okay, and so what I have done, I have taken model analysis module in ANSYS Workbench. Okay, and then we have imported this geometry, fan blade geometry. Okay, and then I have assigned this with the structural steel. So this material is assigned with the structural steel. Okay, then I have done a meshing for it. We have not defined contact because there is a single body. Okay, then I have applied displacement boundary condition on this face. Okay, so to apply displacement boundary condition, you can come here in the model, insert, and then you can apply displacement, and then we can select the face. and then x, y, z translational degree of freedom. From here we can control. Okay, so I already have a displacement boundary condition applied here. Okay, and I have fixed x degrees of freedom. Okay, so before doing this, what I will do, I'll suppress this boundary condition. Okay, and suppress this. If we don't have any boundary condition applied, there is no boundary condition, this body is free. Okay, and now if I try to solve this, we observe that all first 6 degrees of 6 modes or 6 natural frequencies are very close to 0. Okay, and if we try to look the deformation behavior, okay, if this is the first mode, and if I try to play the animation for the first mode, you can see this is moving freely. Some motion is in z direction, also there is some rotation. Okay, so this is not a single mode. In the second case, we can see this plate is freely rotating about z, and also there is some displacements also in this direction. Tilting is happening. Here also we can see this is the third mode, this is the fourth natural frequency, and this is the fifth natural frequency, and all the natural frequencies are very close to 0. Okay, because if you look at your natural frequency is equals to under root of a stiffness by mass, and since this plate is not constrained from any point, it is free in space, the stiffness, there is no force required to move it in any direction, so that's why in a space the stiffness of this is 0. So that's why we are getting all the natural frequencies as 0. Okay, now if I unsuppress this and only fix x deformations, x directional degrees of freedom, x degrees of freedom, and then solve this analysis. Now we see that we have two natural frequencies, fifth and sixth, which are non-zero. Okay, so if you look at the first mode, this is at 0 frequency, this is moving freely, this is moving freely, this is also moving freely, because we have applied boundary condition in here, and this is moving at this case also. And in fifth, when we see, if we look at this face here, we can observe that this face is not moving in x direction, this is constrained in x direction. Okay, and also if we look at the sixth mode, we can see that the plate or the fan blade is twisting, but at this point this is not moving in x direction, and it's kind of rigidly fixed here. It is not moving up, because right now if you look at this scenario, we have only said that don't move in x direction, but this faces should have gone up because of the twisting. It should have gone up, right? Because since if we look at here this way, we have the plate, and the plate is trying to rotate in this fashion, okay? And if we have a node here and it has to rotate with respect to that, it has to go from this point to here and this point to here. So if we look, then we will find that to have this, to achieve this rotation, this node here has to move in x direction, and this node here has to move in x direction. But we have applied the boundary condition that this face should not move in x direction. So we have just applied the x direction constraint, but by virtue of that, it is also not allowed to rotation of this kind of rotation is also not possible because of just x deformation. That's why even if we are constraining this in only one direction, x direction, we are getting two modes, two natural frequencies, saying that there is a more than 1 degrees of freedom which is fixed. If we go and try to look the same thing in case of remote displacement, if we just fix the x degree of freedom in remote displacement, then we will find that we have just one natural frequency which is non-zero, which is 264.9, and same result we have in the displacement scenario also, but which is a fixed mode, and there is an additional mode which is an additional stiffness or constraint coming to the geometry because of the displacement boundary condition, which is not present in the remote displacement. And why this is not coming in the remote displacement, if you want to understand, so we have this as a displacement condition, okay? Now if you look at the remote displacement case, as I have told you, the remote displacement is one RP is created at this point, okay, and these nodes are having constraint equation with respect to this RP point. Now if you want to rotate, when you apply the boundary condition in case of remote displacement, only the boundary condition is applicable to the RP. So the RP should not move in x direction, but these nodes can move maintaining the constraint equation. If the constraint equation is maintained, so the constraint equation, for example, is that the distance between this should be same always. The distance and distance between this should be same always. Even after rotation, they can maintain this distance. Okay, and this point still can be in fixed position in x direction. So in case of remote point, we observe that we don't have that non-zero other than 1. If you are fixing only 1 degree of freedom, we get only one non-zero value. Similarly, if we fixed all other degrees of freedom, we can see I have done these calculations by myself, and if you have all degrees of freedom free initially in both the cases, in displacement and remote boundary condition, remote displacement cases, the degrees of freedom or model analysis results are 0, same. Okay, now in case of x, if you make only x fixed, we have 2 non-zero value. If you fix xy, we have 3 non-zero value, and if you fix xyz, we have all 6 non-zero value. But in case of remote displacement, if you are fixing 1, you have only one non-zero value, because this is coming because of the constraining the boundary condition in x direction. Now in second case you have two fixed constraints, so you have the stiffness coming from the fixation of the remote point in x direction and y direction. So you have 2 degrees of freedom. If you're fixing x, y, z, you have 3 non-zero value. If you have x, y, z and rotation in x, then you have 4. If you're fixing 5 degrees of freedom, then you have 5, and if you're fixing all degrees of freedom, you have 6. So again, if you see these results for all degrees of freedom fixed in RP remote point has the same result as a only fixing 3 degrees of freedom in case of displacement boundary condition, which eventually means that even if you're only fixing 3 degrees of freedom, all other degrees of freedom are automatically getting fixed, because there the boundary condition is applying on the nodes of the face, and since the face is in plane or is a line, the relative displacement is not possible because of x constraint. It cannot move in y and z direction similarly. Okay, and here we can see like this value are exactly matching, very close also. In case of like here we can see 264.99, 264.9, 168.53, 168.52. So we can get same result from the displacement boundary condition and the remote displacement boundary condition also, but not always. When we want to have a higher freedom or to control the degrees of freedom, then remote displacement is a better option to use. When you already know that something is completely fixed or all degrees of freedom, you already know that the rotational won't be happening there, then we can go for displacement boundary conditions. Okay, and that's why the boundary condition, applying the correct boundary condition, is very important in getting the correct result from our simulation. So hope you understand the difference between the displacement and the remote displacement boundary condition. Please let me know if you have any question in the comments. Thank you very much.